Right, so the title is High Energy Harmonic Maps. I'll be discussing two joint works. One is with Peter Smiley, who's a junior professor in Leipzig. The other is a joint work in progress with Sarah Maloney, who's a professor in Virginia, and her graduate student, Lam Nguyen. I've sort of taken portions from both of these works, which I think fit into a common theme. Okay, so the starting point of this talk, at least for this audience, would be the non-abelian Hodge correspondence. So throughout the talk, X will be a fixed closed Riemann surface of genus at least 2. And to me, the non-abelian Hodge correspondence is an identification from the representation variety to the moduli space of G Higgs bundles. And in this talk, I'm mostly just considering stable or polystable objects. Okay, so we've discussed this a number of times already in the conference, but I thought it'd be nice to review how to go from this side to this side, at least some of the perspective I'll be interested in. So you start with an irreducible or reductive representation rho from pi 1x to G, and then a theorem of Donaldson and Corlett allows you to produce a rho equivariant harmonic map to the symmetric space F. And I'll denote my symmetric space by G mod K. So K is the maximal compact subgroup. And out of this, we produce a G Higgs bundle. So just for those that aren't maybe familiar, there's a number of equivalent definitions of harmonic. But the definition that's probably most suited to this topic is as follows. It's a solution to this second order semilinear PDE. So you consider the 1,0 part of the derivative of F, and then you apply the 0,1 part of the pullback Levi-Civita connection. Okay. There's plenty of other perspectives, such as minimizing a Dirichlet energy. So we write this out locally with a coordinate, let's say Z. We get del squared F over del Z bar del Z plus some first order term. And so it might be helpful to know that if you replace G mod K with a Euclidean space, this term vanishes and this becomes the ordinary Laplace equation. So you can think of a harmonic map just as a mapping between manifolds that generalizes the notion of a harmonic function. And if you don't have intuition on harmonic functions, the intuition to have in this topic is that the Z derivative is holomorphic. The del Z bar vanishes. Okay, so once we have the harmonic map, the Higgs bundle is just some data you associate to it. So P is obtained by pulling back and complexifying a bundle over the symmetric space. And then to get phi, one takes del F. And so this is a 1 form valued in the pullback of the tangent bundle complexified. And this identifies, at least assume my group is complex, with 1 forms in the adjoint bundle. And under this identification, we refer to del F, or we call it phi. So we should think of the Higgs field as just the 1,0 part of the derivative of the harmonic map, which is, if you go back to this perspective, this is some geometric realization of your representation. Okay, so that's a little review. And the question that I want to address in this talk is, what does F look like when rho, the representation, or P phi are near infinity or large? So what do they look like when you kind of go to go to infinity in the moduli spaces? And on the motivation, I'll be fairly brief. Just very broadly, we want to understand the character variety, the moduli space of Higgs bundles, and the non-abelian Hodge correspondence near infinity. So as we've seen, representations can encode geometry, and one might be interested in studying how that geometry degenerates through the harmonic map. The moduli space of Higgs bundles carries, a rich geometry, and there's been a lot of work on studying the ends of the moduli space. And as well, one might ask, how might the non-abelian Hodge correspondence extend to various compactifications? So So this question, I think, is sort of tied in with all of these things. Okay, so right away, I'll give you the heuristic that I've learned. What we need to know about the symmetric space is that this is some Riemannian manifold on which G acts isometrically, and it has non-positive sectional curvature. If G is SL2C, then this is the hyperbolic 3 space of constant negative curvature. But in general, it's just non-positive. So in particular, G mod K has flat subspaces, just being flat isometric copies of Euclidean space, and these have dimension equal to the rank of G. And if you're not an expert on, if you're not so familiar with Lie groups, you can take this to be the definition of the rank of G. Okay, so to keep us grounded, the main example to have in mind is G being SLNC, and then G mod K identifies one model for this space is matrices A and SLNC that are symmetric and positive definite, equipped with the Killing metric. And an example of a flat is just the diagonal matrices that have, the positive entries. Okay. So now let's, sorry? Yeah, sorry. My bad. Thank you, yeah. Okay, so now we begin our heuristic. So let's start with F, which is an equivariant harmonic immersion. I'm going to make an assumption, which is that the area is large. So this is the pullback of the Killing metric, and this is the area form. And this 2 form descends to the surface and can be integrated. If your rho is acting properly discontinuously, so that the quotient of the symmetric space by the action of rho is a manifold, and F is an embedding, then this would be the area of the surface that descends to the quotient. So this is a reasonable notion of area. Again, if it's an embedding, this is just the area of the image of a fundamental domain. Okay, so we're going to assume it's large. That's something that could certainly happen when the Higgs field is large. It doesn't always happen. If you're a Fuchsian representation into SL2R, then the area is constrained by Gauss-Bonnet. But we'll assume it's large just for the sake of giving a clean heuristic. Okay, so an application of the Gauss formula for curvature shows that for a harmonic immersion, the Gauss curvature is always non-positive. And then we apply Gauss-Bonnet, and this tells us that the average Gauss curvature, this is just minus 2 pi times the Euler characteristic over the area. And for a large area, this behaves like minus the area to the minus 1. Okay, so these sort of innocent facts suggest the following: that for area large, F should mostly cling to the flat subspaces. So to elaborate on this, the curvature has a consistent sign. So in this integral, there should be no cancellation. And this is saying that on average, the curvature, if the area is large, then should be very close to 0. So what we then expect is most of the time, it's near 0, so it should be near a flat subspace. Okay, but the word mostly is doing quite a lot of heavy lifting here, because there's still some definite amount of curvature prescribed by Gauss-Bonnet. And because this is an L1 norm, what we expect is that the curvature concentrates in certain isolated regions. So at some point, it runs into some region where the curvature is exploding, and it's looking very hyperbolic, and I can't draw a picture. So I'm not sure what happens there. But afterward, these are isolated anyway. So what you could expect is afterward, continues to be near some flat. And what I've drawn here is, it's close to the flat and looking kind of flat, then it approaches a mystery point, and then afterward it's traveling to other flats, but I'm allowing it to maybe transition into multiple flats at once. It could go into, it could be touching 3. Right, and what we draw from this is that f then should behave like a harmonic function. From the universal cover to r to the rank of g. So if f is very close to a flat and it's harmonic, then it probably looks like a harmonic map into the flat. And a flat is just an isometric, totally geodesically embedded copy of r to the rank of g, so it should just look like a harmonic function to r to the rank of g. And so that's a heuristic. I'll just mention, there was a nice application of this heuristic, and that was counterexamples to a conjecture of Francois Laborie. So this conjecture was about uniqueness of minimal immersions for Hitchin representations, and using intuition that stemmed from this, we constructed minimal surfaces in higher rank symmetric spaces that resembled unstable or non-area minimizing surfaces in Euclidean spaces, which led to counterexamples. So that was one application. Okay, so stepping back, our original question was, what does a harmonic map look like near infinity? And we have this picture that I kind of find appealing. So it suggests a refocusing of our question, and that's the following, say, research project. I think I'll ditch this line. And that's to just make this picture precise. I keep drawing it when I give talks, so I, over the years, have just wanted to do that. Right, and I should mention now that there's a number of works by Katsarkov, Noel, Pandit, and Simpson that I'd say maybe fall into this project and that have been a consistent resource and inspiration. And there's been sort of a lot of work on this topic, and probably the earliest work for SL2R is due to Mike Wolf and Yair Minsky. And these were maybe the first papers I read in graduate school, or the first papers I was able to read. Okay, so I can also now kind of say a bit more about what the works are about. So in the joint work with Peter Smiley, I'm going to tell you what happens when you're close to a flat and what we can say in total generality. And then in the joint work with Sarah and Lam, I'll tell you what happens here in an extremely special case. Okay, so I think we can jump right in and set up the first work. So let P phi be a Higgs bundle, a G Higgs bundle, with phi not nilpotent. And we're going to consider rays are going to P R phi, with R being a positive real number. And these come with equivariant harmonic maps. I assume I'm working with a stable Higgs bundle on a closed surface, and these all come with equivariant harmonic maps, let's say FR from X tilde to G mod K. So since the Hitchin vibration is proper, and we're not nilpotent, this is certainly blowing up in the moduli space. I should also mention if these are minimal, so conformal and harmonic, then the area behaves like R squared. So we're in the position of the heuristic. Okay, so we want to compare FR to a map to Euclidean space. And I'm going to let pi from C to X, and I'll write the universal covering as pi tilde from C tilde X tilde be the cameral cover. And F phi from C tilde to R to the rank of G, the cameral harmonic function. So I don't assume people are familiar with the cameral cover. and I'm going to define it carefully, or describe it carefully, after stating the theorem. I also just made up the word camera harmonic function right now, so I don't assume people are familiar with that either. But it's not too hard to guess. Once I write everything out, I'll also define that. Yeah, okay. So here's the first theorem I want to present. So I should say this is, I attribute a case of this theorem, I guess sort of the generic case for generically regular semisimple Higgs bundles, which I'll also define, to Takuro Mochizuki. So he wrote a fairly influential paper about solutions to the self-duality equations for certain harmonic bundles. And he doesn't write much about harmonic maps, the geometry of harmonic maps, but if you plug in his analysis, you get the result that I'm going to write in. Okay, so, but sorry, you get in this case. So the theorem is that there exists a discrete invariant subset, B tilde, contained in X tilde, such that for any disk, let's say U inside the complement, we have the following comparison. Oof. Great. Okay, so let's dissect this statement. There's some invariant subset B on X tilde, so it descends to a subset B on X, where you can compare FR to a harmonic function. So what I'm not going to say carefully is what the tilde means. But I'll say in words, it means that FR is close to a flat in some C0 sense, and its intrinsic data is comparably close to that of some harmonic function that I'll define for you. As well, we have sharp error estimates. And so for generically regular, so in general, yes, for generically regular semisimple Higgs bundles, this is exponential, but in general, you've got this bounded error term. And as I said, the GRS case is mostly due to Mochizuki, so our contribution here is handling the general case in which we've got this extra error term. Capital R, oh yeah, sorry. It's on the other board. So I take the Higgs field P R phi, and R is just a real number that I'm taking to infinity. Yeah. Okay, so I could pause for questions, but probably I should define the cameral cover first and the harmonic function of interest. Oh, this is distance from Z, from your point Z, to this bad set B to the power of -2. Yeah. It's very common to want to rescale also the target by R. In this case, you get a quadratic, a term that's going to 0 with R. Okay, so I'm going to define these things in the case G equals SLNC. Yeah, phi is fixed. Yeah. So in fact, I could write it out very precisely, and we don't really consider rays. What matters is gaps between the eigenvalues of but I think this is just a more palatable statement, yeah. Really, it's a result about Higgs bundles harmonic metrics on the disk, but I'm just putting in this context. Okay, so I'll explain things for G equals SLNC, and hopefully in a friendly way for someone who hasn't studied Higgs bundles much before, or Lie groups, because that was the setting, or at least my my setting when I learned all this. So GRS means generically regular semi-simple. So that means there exists some discrete set B contained in X, such that locally, on let's say a disk V contained in the complement, if we write phi as 5z dz, then it's diagonalizable with distinct eigenvalues or eigen-1 forms, depending how you want to look at it. So here, so phi is just a holomorphic matrix in Z with a dz attached, and so you can diagonalize it, and the diagonal entries become one forms. And so these are one forms on X, and really generically semi-simple means you can do this, and generically regular semi-simple means they're distinct. Okay, and so why is this useful when thinking about harmonic maps? Well, since del F is equal to phi in some sense, by integration we see that F lands in a flat if and only if this diagonalizing matrix is constant. That's the connection there. So, this is inside a flat subspace, and if this were constant, then F would just be on the nose inside that flat. But it does tell us, although that shouldn't be true, it gives us something to compare F to, a harmonic function. So locally, we could define, I'll call it F phi hat, from V to this hyperplane in Rn, which just identifies with Rn minus 1, and here n minus 1 is the rank of SLN. We obtain a harmonic function just by integrating the real parts of these one forms from a fixed base point. So the real part of any phi I is a harmonic one form, and integration just gives you a harmonic function. Right, so this is a harmonic function that serves as something to compare F to. And really the content of the theorem is just that you're close to this function, but we can globalize and think of this as a global object. So how to do that is I draw a picture of my surface, and here's my coordinate patch. If I traverse around a loop, or just do any coordinate change, at worst what's going to happen is it'll permute these phi i's. The eigenvalues stay the same, but maybe their order changes. So you can't necessarily globalize, but there does exist a branch covering. This is just basic theory of covering spaces. There is a branch cover, we call it C for the cameral, well, C to X, on which phi 1 down to phi n lift the global one forms. It might not be right to call this the cameral cover, it's really a component of the cameral cover. Yeah. Okay, and then we just define F phi from the universal cover to Rn minus 1 by integration. And so this is our candidate harmonic function to compare the harmonic map to. So I'm not going to tell you about the proof. All I'm going to say is that it's by the maximum principle. You have two solutions to elliptic PDEs, and you want to compare them, and this would be a typical approach. It's of course rather delicate, and it's something that I'm not going to discuss today. Okay, so that's the generically regular semi-simple case. And in the general case, what do you do? Well, so the paper was just published, so I can admit that it's not that hard in principle. What do you do when you have a matrix that's not diagonalizable? Is you take the Jordan decomposition. And so one can write your Higgs field uniquely as a generically semi-simple Higgs field. And a commuting nilpotent Higgs field. So there's something delicate happening here. The naive thing to do is take the semi-simple part in each fiber, but if you do that, these won't even be meromorphic. But it turns out there is a way to canonically split a Higgs bundle with the subtlety that they're in general meromorphic at a certain set, but I'm not going to address those subtleties. And then we just define F phi as before, using the generically semi-simple part of the Higgs bundle. And we obtain our comparison map. So again, I'm not going to, the proof is analytic in nature, and it's an analysis of the self-duality equations. But sort of the key point is that in order to, you want to control the error between your harmonic map FR and the Euclidean harmonic map. And so it amounts to showing that the nilpotent part only contributes a bounded error. And there's some interesting ingredients in there. So I'll just highlight one of them, which I thought sort of intriguing. So this is maybe more technical statement. So away from the bad set B, which is suitably defined, if I call HR the Hermitian metric, solving the self-duality equations, one can show that R phi GS adjoint with respect to HR, R phi GS goes to 0, exponentially in fact. And same if you pair this with the nilpotent part. And so what you get is a sort of asymptotic decoupling of the Hitchin equations. So you get that the curvature of your metric plus the commutator term with the nilpotent part of your Higgs bundle goes to 0. So what this is saying is that as you take R off to infinity, the solution of the self-duality equations for R phi nearly solves the self-duality equations for the nilpotent part. And then really the way the proof goes is you say this is nearly a harmonic bundle, and you can apply the argument for properness of the Hitchin fibration, since this is nilpotent, and you essentially have the PDE. You can also do Uhlenbeck compactness and show this converges in some sense to a nilpotent harmonic bundle in the limit. So I find that kind of curious. Okay, so that's actually the first part of the talk. I'm happy to pause for any questions. Yeah, I thought it did at first, but it is contained in the ramification of the caramel cover. Yeah. There's this little, there's a subtlety if you're working in SLN versus G because the representation can introduce more bad points, but if you're working with a principal G Higgs bundle, then yeah, it's contained in there. Okay, so I just erased a picture. Oh, and I should also say, if I redraw my picture, just to explain this bad set B, so if you're in a diagonal, if you're diagonal and all of your entries are distinct, that means that's the unique flat that you lie in. But if two entries match up, then you're actually containing infinitely many flats. So at a point there where these eigenvalues match up, this is where it's totally reasonable to transition into different flat subspaces. And so the meaning of B also matches up with this picture. All right, so I think we've sort of totally understood the intrinsic asymptotic geometry of these harmonic maps. So the main question to address then is what happens at the set B? So this bad point here. Okay, so the standard approach in geometric analysis would be to do the following. So take U to be a ball around P and B with a coordinate, let's call it Z. And so we write now R phi, still in this setting, locally as, let's say, R phi 0 Z dz. And the standard thing to do is change to a coordinate, let's say ZR, such that in this coordinate, R phi is now phi 0 ZR dzr. So we normalize the Higgs field in our coordinate. The picture here is, here's my subset U, that's mapping in this thing over here. We don't really know what it looks like. But then I'm pulling it back to a really big ball over here. And then on this big ball, the Higgs field is staying bounded in the coordinate here. Okay, and then you can then take R to infinity and let this ball grow. And so as R goes to infinity, FR converges in some sense that can be made precise to a harmonic map, let's call it F infinity, from C to G mod K. And that harmonic map from C tells you what's happening over here. And so this tells us that what we need to study is just general harmonic maps from C to G mod K with certain properties. I guess the comparison to make is with what's called bubbling in geometric analysis. So one of the most earliest examples of bubbling is when you have a sequence of pseudo-holomorphic curves of bounded energy. And either they subconverge on a subsequence, or energy concentrates in small regions, for which you then get what are called bubbles. So here is very similar, except now we have a concentration of curvature rather than energy. So one can think of these maps from C to G mod K as some sort of harmonic bubbles. And our question really is just, what are the bubbles? What do they look like? So there's been quite a lot of work in this direction for various groups. But it's been sort of irking me that the case of SL2R was never sorted out fully. And so this is the subject of the work in progress with Maloney and Nguyen. In this case, just a reminder, G mod K is just a hyperbolic two-space with a metric of constant negative curvature. So we want to understand maps from C to H2. And my starting point here is results from Hitchin's original paper on the self-duality equations. And I'm going to state it in a way that's surely different from where it was how it was stated there. And that's that an SL2R Higgs bundle is stable or polystable on X is equivalent to a pair QD and so Q is a holomorphic quadratic differential and D is a divisor that's dominated by the divisor of the quadratic differential. So here, this just spits out n if Q has a 0 of order n and 0 otherwise, or if Q at Z and 0 if Q of Z is not equal to 0. Okay, so at this stage, I'm going to kind of stop talking about Higgs bundles entirely and just think of this in terms of harmonic maps. So in this setting, Q is called the Hopf differential. And if I write it in local coordinates, since I have a global coordinate, this is the metric on f of z, and then fz bar bar, dz squared. And one notices that d is the divisor of fz. And so it's clear that this divisor is dominated by the divisor of q because you have a factor of fz in the definition. And also in this context, the bad set B is just a 0 set of Q. And finally, around any 0 of Q, we can find a coordinate Z such that Q is just Z to the n dz squared. So what this tells us we need to understand is just harmonic maps from C to H2 with Hopf differential Z to the n. Okay, I told myself if I were under 40 minutes, I would state the more advanced theorem. And I'm 40 minutes on the nose, so why not? So the first thing to do to understand the geometry of such maps is to prove an existence and uniqueness theorem. So I'm just going to work in full generality for fun. So Q of Z dz squared is any holomorphic quadratic differential on C, and D is any divisor dominated by that of Q. Then you can find a unique harmonic map, and unique is up to isometries of the source and target. So unique harmonic map from C to H2 with data QD. There's an extra condition, so such that sigma of H Z of Z dz squared is stochastically complete. And I'll say what that is in a moment. The case that we actually care about is polynomials, or really Z to the N. So for Q, Z a polynomial, uniqueness always holds. Okay, and before I talk about the results, I should just mention the case D equals 0 is been known for a while. This is due to Au and Wan in 94. And this extra line that uniqueness is automatic for polynomials is due to Chongling Li in 2017. Yeah, so I'll get to that. So it means, okay, it's a sort of technical condition, but what it means is that if you run Brownian motion on your Riemannian manifold, then it runs for all time. So it comes from that, a different sort of family of theories. But really all that we're using here is that if you're on a stochastically complete Riemannian manifold, you have access to a number of maximum principles that are used to prove uniqueness theorems. And for this line about uniqueness always holding for polynomials, one just has to verify that for a polynomial, you always have stochastic completeness. Right, so this result was always already known in the case when D is 0, and in that case, this was also a diffeomorphism onto its image. So I won't say much about the proof. Essentially, one sets up Hitchin's self-duality equations, and one has to solve them. The method of existence the typical method is called the sub and super solution method, and it's been done in many contexts before. The only difference here is that this divisor introduces singularities into your solutions. But still, it's the kind of thing where, if you have a strong grad student, you can send them all the references and kind of say, use this method, and then send them away for a month, and they'll come back with an existence theorem. The uniqueness, we didn't know about the stochastic completeness, and the normal methods. Also, let's just say about existence, you can probably get this I think you can just get this by applying some results of Lee and Mochizuki as well. But for the uniqueness, some new idea was needed. So that's where it's helpful to have like a really, really strong grad student. Then it'll work better. Okay, so what I'm most interested in is the geometry of the situation. And I'm going to specialize now to polynomials because we're most interested in Z to the N. So let's start off by looking at the most basic case we can do, and that's Q equals dz squared. So here we have C, and I'll call my coordinate x plus iy. Does anyone know this example? Oh yeah, I see someone nodding. So you just take x plus iy to x. And so you collapse this onto the line, and then here's my hyperbolic space, and then I just isometrically identify this with a geodesic. And it'll be helpful to draw a picture just to point out that we have horizontal lines that are being sent to this horizontal, and of course vertical lines that are all getting snapped to 0. Okay. So for non-degree 0, this was investigated in the diffeomorphism case by Han Tom, Tribergs, and Juan in 95. And so let's say Q is PZ, dz squared. P is a polynomial. And the degree of P is positive. And we're in the case of divisor is 0 of that theorem. Then the unique harmonic map is a diffeomorphism onto an degree. I'm going to make n bigger than 0. And so this is a diffeomorphism onto an ideal n plus 2 gon. So an ideal n plus 2 gon is where you just pick n points on the boundary of a hyperbolic space, cyclically ordered, and you just connect them by geodesics. So that's an ideal triangle. And here's an ideal pentagon. Okay, so let's give some idea why this is true. So let's take QZ is equal to Z cubed dz squared. So here's C. And at a point P not equal to 0, we can find a coordinate, let's say W, such that Q is equal to W squared. We can always change our coordinates in this way. So here's my W coordinate. And I'll draw the horizontal curves in yellow and the vertical curves in blue. And I'll label this as C plus I eta. And we get a patch in here in which your dW squared. And now we have images of these horizontal curves and the vertical curves. So one thing to notice about these curves is that the images in here are independent of the choice of coordinate W. So the curves where C is constant, where eta is constant. So these are the horizontal curves. They give a singular foliation of C. So all that means is a foliation where you have a singular point. If I draw it in yellow, maybe I'll erase the axes. It looks something like this. And so these are the images of all these horizontal curves. And so now if we go far away, let's say go far from a 0, the harmonic map, I called it H. It should look like the harmonic map with Q equal dW squared. So if I go very far away from the 0, in the limit, it looks like I'm just a harmonic map on C with the Hopf differential dW squared. And so this implies that the curves eta equals constant. These things become, under the image of our map, they become nearly geodesic. Since the map with dW squared takes these curves to a geodesic on the nose. And the vertical curves, they get nearly crushed because the dW squared map just takes those to a point. And so the picture that we get from here is we see these yellow curves. They're in the limit, they should give you a geodesic. So I get a geodesic connecting here. And then over here, I should get another geodesic that has a shared endpoint. And because this is a diffeomorphism, they connect quite nicely, and I get this ideal pentagon. Okay. So now one wants to understand the geometry in the case where the divisor is non-zero, and we should start with the simplest examples. So first we could take z dz squared. So the options we have here is our divisor could be 0 at 0, or it could be 1 at 0. So this is the case we just saw, and this is an ideal triangle. In this case, you have f of z is equal to 0, but the z bar derivative is not 0. And if you think about it for a second, you can just take this map and precompose it with conjugation. So that's easy. The next is z squared dz squared. And so you have 0, 1, or 2. The first case, we have our diffeomorphism to an ideal square. And in this case, we have the orientation reversed. Any guess for this? So what we know is, I guess what I'll say is that this type of behavior is still the same. It's cut up into regions, and these sectors are sent to geodesics in the limit. Or in other words, you're supposed to take 4 points, you choose 4 points on the ideal boundary, or you're given 4 points on the ideal boundary, but you don't really know what those points are. So in this case, you actually just get a geodesic. So what you get is the geodesic composed with the map z going to z squared. This is still a harmonic map, and it's not too interesting. The other case that one could do fairly swiftly, so there's a lot of cases to ignore. You can, once you go past n over 2, you can switch everything back with z bar. But so one case to know is d0 equals 1, and then you have a branch cover of this ideal triangle. So the first case that isn't either a conjugation or a covering of a known case is q of z is equal to z cubed dz squared, and the divisor point at 0 is equal to 1. So what you get is 5 points on the boundary of the unit circle, but some of them might overlap, and you don't really know how you connect them up. So the hint one would give is that this has a branch point of order 2 at the origin. So it's doing sort of twice a rotation compared to what it should be doing. And so what you get for this one is, instead of a pentagon, you connect every other point with a geodesic. So you get this pentagram, which is, I think, rather pretty. Okay, so that's sort of the general theme for z to the n. And so here's what we have. So first case is the rotationally symmetric case, z to the n dz squared. And I'm going to assume d of 0, which I'll call m, is at most n over 2, because I can get to the other case by complex conjugating. I write n over 2 over m plus 1 is r dot k over r dot l, where the GCD here is 1, so they're coprime. And so then h from c to h2 takes the form h of z is f of z to the r. And I'll tell you what f is when I erase the board. And so f is a harmonic map onto what's called a KL ideal star polygon. So it turns out these are classical objects in geometry that have been studied for a long time. So what is that? I'll do 7, 3. So you choose k points on the 1, 2, 3, 4, 5, 6, 7 on the boundary of the unit circle, and then you connect every L of them with a geodesic. So this is very amusing for me. So 1, and we get this thing. Okay, so that's really the main case of interest. But there's another case where we can say the answer, and it's kind of nice. So again, QZ is PZ DZ squared. And I'm going to assume 2D, well, the condition is 2D is at most Q. The original condition was D is less than or equal to Q. And so this occurs if and only if F is a branched immersion. So there was a paper of Bradlow, Biswas, Dumitrescu, and Heller, where in a different language, they observed that this condition is necessary for your map to be a branched immersion, and they proved that a stronger condition is sufficient. And so it turns out this holds in general, and for maps from C to H2. And so in this case, the image of F is just the region bounded by the geodesics connecting the endpoints. So you draw any collection of points on here, and then you connect them up in any order you want, as long as you're preserving the orientation. So something like that could occur. And in fact, using a result of Subhajoy-Gupta and Govinda-Sao on maps from C to H3, any configuration occurs. When did I start? Do we know how much time I have? Oh, okay, cool. Well, I'm mostly done. I think I'll just say that this is kind of falling away from the theme of high energy harmonic maps, or maybe it falls into other rays that aren't the ones we've been looking at. But in general, it's sort of pathological, and you get a lot of different looking shapes on the disk that aren't so nice. So just for E of degree 2, one example that we have is what's called a folding of a ideal square. So let's say I have this point and this line, and then this line and this line, and they get identified here. And so what the map does is it, on this part of C corresponds to this triangle, and then it folds back on itself to give the same triangle. Another example that we have is these two triangles kissing. So in theory of singularities, this is called a collapse line. But then there's kind of worse looking examples. So one we have is you connect these up, but then these are connected by a curve that's not a geodesic, and then you get another triangle on here. So this might be called shearing. Oh, sorry, without this condition. So if the map isn't a branched immersion, it should have some lines on which it's rank 1, and then it's a lot harder to understand the image. Okay, and so I'm out of time, so I'll just say the application, going back to our original theme, is to harmonic maps to our trees and the Morgan-Schailing compactification of the character variety. So if you have a family of maps, let's say FR, to the hyperbolic space, but then you rescale the metric by R, this in some sense converges to a map F infinity to a tree. It's called an R tree. And people have wondered for a while, how do you describe the limiting tree in terms of the Higgs bundle data? And so having these star polygons is what's letting us do that. When you do the tree, you get the triangles in this convergence. Triangles get squeezed infinitely thin, and they become tripods. So in our picture, I don't want to draw it again, but a star polygon with these, the first one I drew, gets squeezed to some sort of prong with 5 singularities. So we're not done the paper because we want to see how far we can get, but we're using this to understand what the limiting trees look like. Okay, thank you very much.
Okay, thank you very much. Are there any questions?
Yeah, hi. So I had a couple of questions. So in these papers you mentioned of Carlos, Alex, Ludmil, and myself.
Oh yeah.
We outlined some similar picture, and there, when we take the limit as r goes to infinity, we also rescale the metric, which I think is what you, in this last
yeah, that's
infinity
what's happening here. Yeah.
You rescale the metric, and then you get a limiting object, which is an R building.
Yeah, exactly.
So I was wondering, in the earlier part of the talk, when you took the limit, you were still mapping into a symmetric space.
Yeah, I wasn't going to a building just in the interest of time, but of course you you could do exactly your procedure. And as you know, a harmonic map to a building comes with a valid chamber valued one form. And from Mochizuki's work in the generic case, that limiting one form agrees with the one you get from the Higgs bundle. And so our work shows that's true in general.
Right. So what I wanted to ask is, so there was, as you mentioned in the end, I mean, there was this interest in understanding when you have the Higgs bundle and you look at its spectral data, that gives you a multifoliation similar to the one that you described here for quadratic differentials. Yeah. And so we showed that the singularities of the harmonic map are contained in the spectral network determined by this, by the spectral data. And I was wondering whether that shows up in this analysis that you do as well. Do spectral networks appear as loci where?
We're yet to look at it, but I'd like to talk to you and then we'll maybe look at it. Yeah.
Because there's this interesting collision phenomenon that happens, which doesn't happen for quadratic differentials, that the singular foliation lines can meet.
No, not for quadratic differentials. Yeah.
Yeah, it doesn't happen for quadratic.
Yeah, exactly.
But it happens in higher ranks.
Yeah. So I mean, we didn't, at least in the second project, we didn't look at higher rank, although actually the existence theorem we proved also applies for certain SL3 Higgs bundles. And we're not going to write it up in the paper, but this theorem there's a version of this for SL3R that might then include the collision lines. Yeah. But that's, I haven't really thought about the details.
I see. And just one last question about this, about the R tree. So if you are away from some, small locus in the space of quadratic differentials, isn't this tree just going to be the quotient of the leaf space of the foliation defined by the quadratic differential?
Yeah. So if you have simple zeros and no saddle connections, then that's true. But exactly the problem with, as you might be aware, is with double zeros, you can have what's called folding.
Yep.
And so the point of this work is for higher order zeros, we want to understand exactly the folding that goes on at the zeros, and also what happens with saddle connections. Right. I mean, there's some understanding of what possible things can happen with saddle connections, but we're trying to get a more precise understanding.
I see. And just one last follow-up question. So is this, you had these special lines in the pictures there. Are those related to caustics?
I don't know what a caustic is, so.
Okay, yeah. We can discuss that.
We'll talk after, yeah.
Okay, I think Oscar was next and then Jack.
So you have this interesting harmonic maps from the complex plane into the hyperbolic plane. So this gives you solutions to Hitchens equations, right, on the complex plane. This is quite interesting. This is quite in contrast to the comment that Nigel made in his first talk, that the physicist, some physicists have found the Hitchens equations back in the late 70s, and they thought there were no interesting solutions, right? So,
it looks cool. Yeah.
So coming to the way they obtained bidimensional reduction from instantons, I guess these are a billion instantons, because this is in SL2R, and so the maximal compact is SL2. So yeah, so you shouldn't trust the physicist, I guess.
Right, I can send them a note with the pictures or something.
I'm having trouble reconciling your pictures. You had this three planes meeting along the line.
Yeah. So
which suggests that your sort of bending is happening on something of codimension 1.
Yes, I did something very
and
bad.
And the bad stuff happens at branch points, which is codimension 2.
So that picture is under the assumption that the area is blowing up, which is exactly not the case of maps to H2. So in that case, that picture should really be some sort of tree-like object.
Okay.
Yeah, that's probably, I was aware of that confusion. I think Mike Wolf has this paper maybe from the early 90s where he gives a description of limits of diffeomorphisms, and it's essentially, ideal polygons glued along geodesics. So one could think in the more general setting, you could have something like these ideal star polygons glued along geodesics. It gets very hard to picture. Yeah.
Any further questions? If not, let's thank the speaker again.